Good afternoon, everyone, and welcome to part 5 of the ASHRAE Ireland COVID-19 mini-series. My name is Daniel Coakley, and I'll be chairing today's session. So just briefly, here's the agenda for today's webinar. So I'll give a short introduction and cover some housekeeping and general information before handing over to today's panelist, Dr. John Gallagher, for the topic of today's webinar, the impact of outdoor environment on natural and mechanical ventilation performance. There'll be about 10 to 15 minutes Q&A from the audience, and I'll finish with some closing announcements by about 2 p.m. So if this is your first time joining this webinar series, I just want to highlight a couple of points regarding participating in the webinar. So by default, everyone is muted. So if you'd like to ask a question in the Q&A session, please use the questions tab in the GoToWebinar sidebar. You can submit questions anytime during the webinar. Ideally, if you can submit them as early as possible, it will make it easier for us to get around to them later in the seminar. If you want to access a PDF copy of today's presentations, they should be in your handouts tab. I suggest downloading these because there's a few slides with a lot of information on them. So there's links on those slides so that you can find further information. And lastly, there's when the seminar is concluded, you'll receive a short survey, which we'd really appreciate your response on. So again, for those new to this series, this was launched as part of ASHRAE Ireland's response to COVID-19 in order to help disseminate guidance to our members. We have a COVID-19 reference section on our website where you can find further information as well as links to relevant guidance from ASHRAE and other professional organisations such as CIBSE and RIVA. And all of the recordings as well are available for our previous webinars on the website. So we've had 4 webinars so far in the series, and they're all available on the website as recordings and also the PDF downloads of all of the slides. So we've been really lucky so far with our speaker lineup since we kicked off the series back in June, and covering a range of topics from indoor air quality monitoring, facility management, ASHRAE guidance, health and HVAC systems. And we're continuing to run the series up until the 24th of September. And hopefully we'll continue to run a further series thereafter. So just as well to highlight, I'm not going to go through everything on this slide. If you want to get detailed information on these topics, you can listen to part 1 of the webinar series where I kind of talk through these points in more detail. This is just some of the resources available from ASHRAE headquarters on COVID-19 response in terms of HVAC systems and buildings. So there's a lot of really good information on the main ASHRAE website, which, as I said, you can link to from this slide. And also, I just wanted to highlight again the ASHRAE Learning Institute, which runs a series of technical webinars and has actually updated their catalogue of online instructor-led training between now and December, some of which are available for free or at a reduced rate for ASHRAE members. So I've just shown all of these on this slide, some of which may be relevant to you. So now I'm going to hand over to today's speaker, Dr. John Gallagher, who's an assistant professor in the School of Engineering at Trinity College Dublin and principal investigator in their specialist air pollution research group. So without any further ado, I'm going to hand over to Dr. John Gallagher. So I'll make you presenter, John.
Thank you very much for the introduction, Daniel. I'm just going to share my screen. So I'm just going to turn on my camera to say hello to everyone, and thanks for the invitation to ASHRAE, and thank you for all of you for joining. I'm going to turn my camera off so that it allows you to see more of the screen and perhaps less of me, which may not be the reason that anybody wants to join. And so I hope you all can see that. Daniel, just confirm that's okay.
Yes, that's perfect. Thanks, John.
Great. So as Daniel said, my name is John Gallagher. I'm assistant professor in the School of Engineering in Trinity College, and part of our air pollution research group that's been running for over 20 years, and I've been part of it for, I suppose, 12 years at this point. And I've been working in the area of air pollution from 2008. And today my talk is around, I suppose, the importance of considering the outdoor environment in the design and of natural and mechanical ventilation. And that has, and I will come upon some of the research that we do in this area around how we take the outdoor environment into consideration in terms of personal exposure to pollution. Obviously, this being part of the COVID mini-series, I kind of want to maybe find parallels between our research on particulates versus aerosols, and how we can learn from and be informed by the outdoor environment in terms of ensuring that natural and mechanical ventilation performance is to the best it possibly can be. So this is a slide that I will be showing in a month or two to our master's students in air pollution, taking a module in air pollution. And typically when we are talking about air pollution, we're talking about what are the different threats and where are you being exposed to the greatest concentrations of pollutants that are harmful to your health. And within that, I always set the question, is it the indoor environment where we spend 90% or perhaps even more during the pandemic indoors, with an array of pollutants that we perhaps don't understand as well. But then there's the outdoor environment where we may only spend 10% of our time, but we can be exposed to the highest concentrations of the likes of vehicle emissions, PM, nitrogen dioxide, etc. But obviously in this current situation, we're dealing with this new threat, this new aerosol that we are now very, very familiar with. This illustration in the background that represents SARS-CoV-2 or COVID-19, and based on what we do around ventilation, I kind of want to discuss the role of the outdoor environment and understanding the outdoor environment and how we apply that understanding to developing better natural and mechanical ventilation solutions. And then to kind of come on towards the end around what are we dealing with in terms of moving forward and dealing with this pandemic. So this is a very nice illustration by the World Health Organization on understanding the size of the aerosol droplets in terms of their transmission in the atmosphere. And if I was to look at the size of the micron size of the particles, they're very similar to the particulates that I would be dealing with from vehicle emissions and general PM or particulate matter pollution that we would be dealing with in our research. So I'm going to kind of look at the parallels between what we do and how we deal with and understand particle transport in a similar context to aerosols. And another very useful illustration, I suppose, that kind of perhaps positioned where I was going to come from today to some degree around ventilation and during COVID, is that there's been fantastic guidance developed by ASHRAE, for one, around ventilation and making sure adequate ventilation is made available, and through mechanical and natural methods. And I suppose where we come from, I always try to think of this, whether or not these two systems work in harmony. Do they work well enough together, and can there be conflicts? And basically today I've kind of prepared the presentation to kind of start off with a context of how I approach particulate pollution or aerosol pollution, as this may be, as a problem, and then give you an understanding of our work and why we approach it from a mitigation standpoint. Then I'm going to kind of discuss the outdoor environment and outdoor exposure, which is actually an area we've worked in for many years, but it informs how we look at indoor exposure. And then look at the steps towards, I suppose, providing the cleaner air, whether it's the outdoor or more specifically today, the indoor environment. And then for a few minutes, maybe give you some innovations in terms of mechanical ventilation and natural ventilation design that we have under investigation, or we have investigated historically, concepts that can help manipulate or engineer the environment so that particles move in the way we want them to, or aerosols in the case of COVID. But I'm going to finally conclude, before concluding, is kind of return to my context, specifically the campus that I get to normally, throughout the previous years, walk into every morning in Trinity College, Dublin, and give you a kind of a flavour of the challenges that we face when it comes to returning to university and ensuring that ventilation is a big part of our face-to-face with students. So from my context, I look at both the outdoor environment, and that's where I historically started, and our pollution group have many years expertise, but we also are very much interested in the indoor environment. And in particular, we're interested in the interface, whether it is a natural ventilation opening, or it's the inlet to a mechanical ventilation duct. And it's those interfaces that, as an engineer, I feel very comfortable at being able to design them, to modify them in a way that ensures that airflow outdoors is kept outdoors, indoors is allowed to escape effectively, or potentially to allow outdoor air from a natural ventilation standpoint to be transported inwards in the most effective manner to maximize ventilation rates and air change rates. So how do we approach these types of problems? Maybe this is obvious to you, but again, a lot of people are very much experts in measurement and measurement of indoor and outdoor environments in terms of air pollutants. So we have many years experience in this field, and it's a very complex. It's not as simple as buying a monitor and positioning it. There's a huge amount of considerations in terms of collecting data in the right location that is representative of a given area, and the same goes for the other environmental variables that are required to develop such use the measurement information for developing models that can then look at scenario analysis around the interactions between the outdoor and indoor environment. And many people are working in that area. So for us, what we've tried to focus on in our work is we measure, we model, but we always want to mitigate particulate pollution exposure. Now, our main focus, and I suppose our pillar that we try to work under always, is passive. If we can, we want to try to develop solutions that are low energy or zero energy. So therefore, we're always trying to look at energy efficiency, as I know previous speakers in the program have talked about. Maybe COVID is now taking away that focus, but we still want to, from even in this COVID environment, want to make sure that we present ventilation solutions that are passive in nature, or really are zero or very low energy. And natural ventilation is a natural preference there. But natural ventilation is a much more complex problem to manage and to control. And that's why we prefer mechanical ventilation, because we can control the conditions. But then when you have something that is controllable and not so much in terms of natural ventilation working together, the question is, are we allowing the outdoor environment to have some level of control in an indoor environment? I'll come on to the kind of context that I feel that we're going to have challenges when it comes to returning to university, specifically in more historical buildings. So really, there's three different kind of contexts and areas that we've worked in, and they all kind of have interconnectivity in the approach that we take. Whether it's a pedestrian on a footwalk in a street, trying to understand airflow and pollutant dispersion in that environment requires a complex level of measurement, modeling, and then also a strategy to be developed around mitigation. And we've done lots of research in the field in that area. But then we've also transposed that into the mechanical ventilation inlets, and my colleagues are leading in terms of designing novel technologies, and I'll show you later, around trying to keep the particulates out. So really what we're trying to do is reduce exposure, whether it's you in the outdoor environment or you being in the indoor environment, and whether the air is being directly or indirectly transported to you in a passive or an active or an energy demanding method. But one area that I feel that we've moved into in recent years is natural ventilation openings in both residential and commercial buildings. And I have just an illustration of a window. However, you could also think about the vents, small vents that are in most rooms in modern homes to allow for sufficient air changes. And what we want to do is stop particulate pollution entering, but also allow a free escape of a given particulate, or again in the COVID sense, an aerosol to escape. So how do we ensure that the outdoor environment is behaving in a manner that allows the natural ventilation to be effective, where perhaps no mechanical ventilation or pressure drop or differences is available or minimal? And a big consideration at the moment is that we're in now summer season, is that opening windows is very feasible. But as we move into the coming months, natural ventilation becomes more of a challenge when it comes to thermal comfort and those other indoor environmental quality factors that we consider a priority also in designing indoor environments. So the context really, just to end on my approach, is that there are short-term and long-term impacts of ventilation solutions. And in the short term, we're dealing with this COVID aerosol pandemic. But in the long term, in the life cycle of buildings, what we're dealing with is a problem that will hopefully not linger, but we still want to have a solution that will continue beyond the pandemic, that indoor air quality is considered a priority. So any changes we make now should have a long-term benefit. And in the context of where we approach the problem, a lot of work around the boundary conditions is what I would refer to of the problem. When you consider a ventilation, and if I recall the figure from a few slides ago around the open window and the aerosols escaping, what you're not considering is, well, what is happening outside that window, and where are the aerosols going if they're escaping? But if you are facing a very strong wind, really, how is that natural ventilation outlet behaving, and how is air change rates being affected in that space? So, and again, this is a historical buildings or older buildings that have combined systems that were not designed in unison, create a lot of challenges in this space. So there's a lot of uncertainty around how we analyze and how we build up the most suitable ventilation system that works and allows natural and mechanical in harmony, or if natural is on its own, to be effective in the pandemic circumstances. So the consequences of change really is what we're trying to ensure. And again, this long-term impact, that we make changes for COVID, will they have positive impacts beyond that? So from an outdoors perspective, even your simple street is a very complex environment. And when it comes to particulate transport or aerosol transport in the air, no two streets are the same. This is a very simple illustration of a three-dimensional street. Forgive the crudeness, but it's just to kind of show that there is some predominant airflow patterns. And really, though, what's missing is that once you add physical features into such a space, you create turbulence, you create additional, more complex airflow patterns that can affect the personal exposure of an individual walking on the street, but also it can affect the ventilation capacity of a natural ventilation opening, for one, a window or a door to a door to a shop or to domestic home, or a window on a first or second floor. And so the more complex the 3D geometry is, the more influential the role of natural ventilation may have on air movements in the home. So just opening a window doesn't assume the air is going to escape. You have to, and I think a lot of people think opening a window in one room will naturally change it, but the outdoor environment in which you're opening that window can have a significant influence. And now, again, this 3D geometry is very simplified, but on a flat roof. But if you imagine that the arrows are traveling from right to left there, the mechanical ventilation equipment on the rooftop can be, and the inlets to those can be significantly impacted also by the transport of pollutants. If you imagine that there is a clean airflow traveling from right to left, and particulate pollution is traveling upwards from the street, then the rooftop on the left is perhaps more likely to receive higher concentrations of PM to enter the mechanical ventilation duct. So some of our work is around developing mitigation measures, barriers, physical structures in the outdoor environment in a street, around trying to improve air quality for an individual. But the challenge is always ensuring that you're dealing with a very dynamic environment. So you want a solution that is improving air quality and not trapping pollution as well to some degree. So trying to create pollution that has a long-term benefit is quite tricky, from and the knock-on effects to the likes of ventilation ducts on facades of buildings is another one. And so the question is then, when it comes to urban morphology, this really complex built environment, how do we design effective ventilation? For example, most recently we've been working around the area of coffee shops, and unfortunately I haven't, like many of you perhaps, I haven't visited many coffee shops recently. We hope that would return quite soon. The idea that ventilation is predominantly into perhaps small coffee shop is through some mechanical outlets, but also the front door or windows provide a strong feature. And the effective design may have incorporated those considerations. But then a coffee shop decides to put awnings and barriers around their outdoor environment and create a kind of an outdoor seating area. And that completely changes airflow patterns. It stagnates the air. It also affects very much the airflow into the coffee shop and out of the coffee shop. And so what's important is trying to understand and consider these consequences, these added components around how they affect indoor-outdoor exchange, and also trying to use them to our benefit. So how do we design it so that we get the outcome that we want? How do we improve the circumstances? And so that's the outdoor environment. Then for our view on indoor, and we try to understand the indoor environment. Now, I should note that some of these illustrations are representative of three-dimensional problems. They're a cross-section of three-dimensional problems, because I've noted over the last few months, a lot of people are undertaking studies around the impact of aerosol transport in the indoor environment, and some are utilizing two-dimensional models. And two-dimensional models serve a role to some degree, but they can significantly misinterpret the dispersion patterns. And for those who are trying to develop ventilation plans, it is a challenge to really do so with two-dimensional models. Now, the truth is that a two-dimensional model is much faster than developing a three-dimensional model by a magnitude to some degree. So in terms of getting results that can inform how we are making this transition to allow for adequate ventilation in this COVID world, it is important that we are thorough in our assessment. So from this indoor environment, one big major thing is the temperature profiles across a space in 3 dimensions, ideally, incorporating the natural ventilation and mechanical ventilation impacts, and in particular trying to understand how the natural ventilation will be used as the seasons change. I think a lot of assessments may be looking at the maximum scenario where natural ventilation is maybe used to its capacity. But as we change into the winter season, this is going to be less likely. So it is important that we take that into account. And also, if we are going to modify maybe windows partially open, then how does that affect air change rates when we have different temperature profiles, not just indoors, but also outdoors? And how does that affect that natural ventilation opening? So from an indoor perspective, the profiles are very important, and the illustration in color on the right is simply a indoor environment, the small box, and forgive the crudeness of this cross section. And essentially, this is where the wind direction to the coming window, which is in the bottom right or the central right wall of the room or space, indoor space, how the natural or the outdoor environment with a strong wind coming at the open window can affect both the transport of outdoor pollution to the indoor environment, which the red signifies a higher concentration, but the location of the concentrations are very different. So it's not an easy problem to consider, but it is important to consider the temperature profiles from an indoor environment, but also the impact of the outdoor temperatures and the wind speed and wind direction in which it may be facing, which may make natural ventilation a very unfavorable option when it comes to trying to improve air quality or allow the sufficient air changes. And needless to say, it's not as if you open a window and you are receiving a clean airflow or continuous airflow across the full area. But in reality, what you have is a very complex, and this is just an example of a particulate matter entering into an indoor space. What you have is a very mixed concentration across the profile. So the reason I want to highlight this is that, as I say, no 2 windows are the same, or maybe that isn't the same whatsoever, but no 2 windows are in the same in terms of how they open and how they allow airflow in. And so the angle in which you open it and the orientation of the window opening and the location of the window opening, all of these factors play a role in movement of particulates from outdoor to indoor, and indeed from indoor to outdoor when it comes to aerosols. And the same is to be said as we've been working more recent years in natural ventilation ducts for domestic buildings, in that all of these different types and designs of openings all affect the airflow patterns in and out of a building, which can play a significant role in trapping aerosols in the indoor environment. So In terms of how we approach a problem, and that's really what today is about, as much as approaching the problem as well as defining a solution, because a solution needs to be tailored to the given environment. There's three kind of approaches in terms of defining indicators or that can help support measurements and what you need to measure to kind of to capture what the outdoor and indoor environments either performing in terms of ventilation or I suppose personal exposure to a pollutant, an aerosol like COVID. Then what you want to do is consider the factors that need to be considered in modeling, because measurement does not solve the problem. You need to understand it more so as well, and the measurement and modeling for us is a combined approach, and you need to collect adequate data to do so. So you need to really understand what factors need to be considered in that. But then lastly, obviously, our role is to try and mitigate. And that's the most important step, and that's where the definitive guidelines that the likes of ASHRAE are now developing are trying to help mitigate to provide adequate ventilation in the indoor environment where we are spending 9/10 of our time. So how do we have to have scientific knowledge around understanding particle transport or aerosol transport. So it's putting these three pieces of the puzzle together that is required to really understand in the specific area the impact of the outdoor on ventilation, whether it's natural or mechanical. And so this is just a very brief example of all the different types of indices, the indicators that are out there for, I suppose, capturing how indoor ventilation is performing or outdoor ventilation is performing. But what we need is also the ability to put the two together and the interaction between the two. And more indicators need to kind of align with one another really to do so. Then when it comes to the factors that you need to consider from the modeling standpoint, and this is work that we've done on trying to capture. Now, this table on the right is valid for natural and mechanical. So some of the factors are very much focused on natural ventilation, but we try to define a set of characters or indicators or factors which influence the design and what we need to incorporate and consider in developing solutions. So I've categorized them as physical or environmental. And really, I suppose today, with this being about the impact of the outdoor on the natural and mechanical, physical and environmental do have a role, such as as I mentioned, the street effect and how air flows around a street and the position of the window within that street. Or the mechanical ventilation on the rooftop and the orientation of the device and the rooftop itself. But the environmental conditions are really around the wind, the temperature profiles, and indeed the pollutant sources. How do we capture and ensure all of these variables are incorporated into models? And suppose I did comment on the left, I suppose I highlighted or underlined the performance of natural or mechanical. So when you're assessing natural ventilation on its own or mechanical ventilation on its own, you have a very specific set of factors that you need to acquire. However, when it becomes more complex is when you have these combined systems and the quantity of data and the boundary conditions of your assessment become much broader and much more complex. So the last step, I suppose, we're kind of drawing upon some of our research that I'll come on to in a moment around trying to understand and use scientific knowledge. And this is just an example of type of scientific knowledge that's out there. And it's around a phenomenon called aspiration efficiency, which we've applied in our research to essentially understand how we can manipulate or engineer solutions to keep particulates out. Or what we have done is also we've reversed the science And as well, if you understand how to keep particulates out of a system, how do you ensure that they also enter a system? And that's where it is very important to engage with the scientific community, and that's where I suppose innovations really take place around solutions. And that's where I suppose ASHRAE is a great community that managed to capture the expertise of industry and academia in developing solutions. So these are just a number of factors, and that's what I want to highlight today, is that there's many different factors, and I think we're not always experts in all of them, and that's where it's really important to kind of work together on developing solutions, whether it's technological solutions or guidance. And what we've done in our work is essentially develop technology that can, and my colleagues really have led in this, is actually reduce the concentration of particulates from the outdoor environment entering the indoor environment. We could stop 1/3 before it even reaches a filter by simply understanding the outdoor environment, by understanding how airflow patterns and air movements occur around mechanical ventilation outlet. What we've now moved on to is also looking, and my main role is looking at natural ventilation in that same area. How can you manipulate it? And the reason we do that is, as I mentioned a lot earlier, energy. We have a scenario where, yes, improved filtration is better filters, but now those filters may have shorter lifespans. We may have an increased pressure drop and more filters are required. And also you may have more energy. So better indoor air quality and through filtration is one way, but if we can provide and supplement a way that passively, without energy, can remove some of the particles, then we can have better indoor air quality with zero additional energy demands. And so filtration is very much an important part of mechanical ventilation, but our approach is to try and support that energy goal while maintaining excellent indoor air quality from a mechanical standpoint. But from a natural standpoint, natural or passive ventilation is now taking space more so as we were looking at buildings. And this illustration on the left is a figure of what will be one of the newest buildings in the university campus of Trinity College. It's our new E3 building, which is currently in the early stages of construction, around how would natural ventilation perform. And so a little three-dimensional model there, you can see some of the windows spread across the faces of the building. And the faces are different directions. The darker shade is at a 90-degree angle to the lighter shade. And you can see the concentrations based on predominant wind characteristics, that particulate matter that would be transported in the air from nearby streets and as road dust or vehicle emissions, could enter in a natural ventilated building through these openings. So certain openings clearly have a greater risk of introducing higher PM concentrations into the building. So how do we then use that information to inform better design natural ventilation? How do you inform the design of novel openings to keep the particulates out and allow the ventilation in? So in a way that we've applied the scientific knowledge around mechanical ventilation design, we're now applying it around natural ventilation design. And I'm going to give a very crude example of that today around the role of a small baffle, a barrier. If you can see that in the right-hand picture, a small black line that I just added to demonstrate. So these two spaces are pretty similar. The orientation is somewhat different, but that baffle significantly affects the inflow of particulate matter into the space. It also affects the outflow as well, and it also affects the flow rate. So you could look at this from a particulate matter concentration or an aerosol concentration that this does, but you could also look at it from a velocity, because what you still want to do is ensure thermal comfort and comfort in general around draft and being exposed to drafts. around how you can design novel natural ventilation openings that are informed by understanding the outdoor environment. And so this is where I'm at, and back to my context. And I'm trying to stay on time, so I apologize if I've maybe ran through some of these slides. But what's fantastic is that we have new modern buildings in our university, and these modern buildings have fantastic lecture facilities for our students returning in the next few months, very much dominated by mechanical ventilation systems, which are very effective and provide the adequate air change rates and ventilation requirements that are set out. However, I am very fortunate, and I still consider my fortune even in the circumstances, to get to teach in historical buildings on campus, like the 175-plus-year-old museum building, which is a piece of art and something I very much enjoy walking into when on campus, obviously. But it's a very complex space in terms of ventilation, even though I won't go into it, but there's a fascinating ventilation story around this room, whereby they are seemingly retrofitted. Any kind of ventilation ducts are retrofitted to windows, so it's quite limited in terms of how it was designed. It was simply retrofitted, and every room is different, and that's one of what this is. Every lecture theatre is distinctive in its shape and size and how air and the type of natural and/or mechanical ventilation that's in it. So the challenge that we face is how do we try to ensure that? And to be honest, there is no clear answer yet, because at the very beginning I highlighted it's almost like a case-by-case assessment to ensure adequate ventilation in these kind of spaces. So in terms of COVID, we're dealing with immediate concern, and I think that's maybe highlighted, to give adequate ventilation. But we always should remember that we have a long-term vision here. If we're making changes and improvements in ventilation, that they are going to play a role in improving indoor air quality or indoor environmental quality beyond the COVID pandemic, when we hope to get back, or we get to this new normal. So the challenge still has to be considered, and as we move through the seasons, will that open window, as the illustration shows, really be permitted? So we're dealing with a very dynamic system. And the reason I think as well, we don't really understand the impact of the outdoor environment, on how natural ventilation openings perform and how it affects indoor-outdoor interactions. So really, when it comes to ensuring adequate ventilation in COVID, it's still a real challenge, and particularly in older buildings that have hybrid kind of Quasimodo-like systems. And for that reason, a lot of our university, well, the current discussion is whether or not masks are going to be part of the return. And really, when it comes to trying to provide an effective solution in complex teaching spaces, then protecting the individual may be a short-term solution. But it's really something that I haven't perhaps, I couldn't say definitively that is the case, but I think the preferred option for me is that we protect the individual from one another, and this way we guarantee that no matter how complex the space, the short-term solution will be effective, and then the long-term solution, as we return to normal, will be effective. So in terms of where we're at, that's my kind of I suppose perspective on the role of outdoor environment and needing to consider it in terms of natural and mechanical ventilation design. Thank you very much for your attention and your time. And I suppose over to you, Daniel, and I'm happy to take questions over the next 10-15 minutes. And also my contact details are here on the slide. Thank you very much.
Thanks very much, John. I'll just bring back on the camera. So there's questions just starting to come in. I was just going to start off with one question I had myself, which was, you mentioned that there's quite a lot of complexity around the design of naturally ventilated spaces because of the the nature of the physical and the environmental characteristics, lots of interplay between different components. So do you think there's maybe a need for better practical guidance and tools to help designers, because not everyone's going to have access to computational fluid dynamic models for every case, especially in small cases like coffee shops that you mentioned? And
absolutely. Complex problems can always be simplified, and indeed they always are. But I do feel that there is a space needed to address this complex outdoor and indoor interaction, and perhaps there is a community that need to look into it in a deep level and then develop very simplified observations. So, for example, the predominant wind conditions. So yes, you could have an array of wind scenarios around a building, but really, if you're trying to deal with the predominant problem, the predominant wind direction, the predominant source, those kind of factors can simplify a very complex problem. And in terms of providing natural ventilation openings around all faces of a building, how do you ensure that maybe the larger natural ventilation openings that are required are on a certain face of the building, maybe the bluff of the building? And the same for mechanical ventilation. So, where is the predominant pollution coming from in the vicinity, and where do you position it on a rooftop, for example? Yes, it's a very complex problem, but sometimes a few simple questions and simple pieces of data can make a marginal improvement, and sometimes that's all we can do is a marginal improvement.
Okay. Thanks very much, John. There's a couple of questions coming in. Sorry, I'm just trying to read through them here. Michael Dawkins asks, any more examples of installations of baffles in naturally ventilated openings to control pollution ingress? Possible variable geometry to suit wind direction or strength, and possibly controlled also by BMS. So
yeah, so that's an area that we're kind of interested in looking into. We actually, in terms of we've always tried to be loyal to passive, and once you start making it mechanical, then you're kind of losing that part of that. But it is something that I think you have to embrace to some degree. There is no formal guidance from an air standpoint, because a lot of baffles or barriers that are placed around buildings are usually for shading. So it was designed for a function of light, and perhaps temperature to some degree, but light. And what a big concern is when you approach that kind of design standpoint, that you are taking into consideration the other factors that a baffle is there. And so the concern is now, if we were approaching it just from an air standpoint and provided guidance, it could contradict the shading requirements that some baffles are put in around buildings. So it is a complex balance, and I suppose that's why different communities need to talk. They don't necessarily always talk, and it is a very complex problem. But no, unfortunately, there's no guidance that I'm aware of around that, and that's an area we're kind of trying to kind of get an understanding of it and come up with very simplified guidance really at this point.
Thanks, John. There's another question here from Shane Dunbar about, well, maybe a comment just regard to the Irish climate and current correct surroundings. The option to naturally ventilate is slightly easier. With a cold autumn and winter on the way, drafts will become an issue, and stagnant air will also be an issue. So there was also a mention of using a weather station or monitoring data for wind speeds and directions to help stop drafts. So I don't know if you have any comment on that and what data you might
Yeah, absolutely. Yeah, so locally positioning some sort of equipment. The main consideration is making sure that your equipment is positioned in a location that you fully understand. Is it being influenced by the local buildings, etc.? Taking readings in a built environment, for example, is very tricky. So it's about your location of it and making sure you understand, is it being influenced by any external, any localized factors that differentiate from, say, taking airport data or some other more another location. So it could influence how you undertake. For example, if you think about a wind turbine or a wind farm, you always take some environmental information there. And so from a ventilation standpoint, is it something we move towards? Or again, with advanced modeling, can we generate synthetic data to provide it, rather than actually even going to the hassle, but the level of work that might be required to collect that information locally?
Thanks, John. There's also a point here about from Don Hoban. So from a COVID-19 perspective, one of the previous speakers in the series mentioned the need to maintain relative humidity between 40 and 60%, or in that sort of range. So how do you naturally ventilate and maintain RH in the winter?
That's a fantastic question. Yes, that's the previous talk, which I listened to very carefully around the RH, or absolute AH as she preferred to define. That's a really good question, and again, that's where natural ventilation and working in harmony, or otherwise with mechanical, or working on its own, you are creating an extremely difficult challenge to try and to keep RH measured. And actually, that's something that I on that very point, measuring RH, or measuring information in the indoor environment, is also a very tricky thing to do. Measuring temperatures, RH, that is representative of the space, especially in larger theaters that are naturally ventilated. Mechanical ventilation, you may get the circulation and you may get good representation from one monitoring location, but natural, there's a huge curveball there, and it needs a lot of informed decision making to put to even measure RH in that right location. So it's a very tricky balance that needs more research in this, and it's not just for COVID, but it's in the long term as well.
Thanks, John. There's a specific question in relation to Trinity College and whether or not you were working with the Choral Society to help return to rehearsals and performance. So looking at I suppose, those sorts of arenas and how those can safely return.
I didn't expect anybody from that audience to be participating in that. No, it's not something that we've been discussing. We've really been trying to discuss that at even department level all my air pollution research colleagues, even just how we're going to manage regular classes. Yes, I suppose there's a lot of concerns around that, where you are potentially aerosol droplets are being transported further. No, I don't have any solution to that. But my concern is that some of the research that's been done, especially, I think I mentioned earlier on about two-dimensional assessments, they are oversimplifying a very complex problem, and yeah, we need to think about it a bit further before we do something like that. I think that's where outdoor spaces might be safer.
Thanks very much, Sean. I suppose just lastly, on the point of maybe mixed mode or mechanically ventilated buildings, there's a couple of points here about the role of air cleaning and disinfection, because of some previous points about the potential spread or aerosol spread of COVID-19 indoors. I suppose, to what extent do you see the role of air cleaning, disinfection kind of playing a role?
It definitely plays a role in addressing this urgent matter, for sure. I suppose one of the reasons I kind of mentioned life cycle in my problem is that we're dealing with a problem now, but the problem will hopefully not linger for too long. And then the air cleaning aspect, is it something that we're only dealing with a problem for the shorter term? And so it's about how do we implement something that may not be necessary for the long term to the same degree as it is now. And for me, that's a tricky balance between technical capacity and economics. And then if we're doing the air cleaning, you know, are the masks necessary? It's a very tricky balance that I don't have an answer to. But for me, there is one element that I do take into account, is that it's very important that we deal with it and effectively right now. But in due course, where do we stand with making changes that might not be cost effective? Maybe I'm not normally one to put my economics hat on, but I do think that that's a consideration for some. Obviously, certain sectors, certain areas definitely need it more than maybe education, perhaps.
Thanks very much, John. There's one other point I missed, actually. Sorry, was I suppose the question was whether there's any way to measure COVID-19 in terms of aerosols in indoor air, which, as far as I'm aware, there's not. But is there any parameters that you would recommend monitoring? I know you mentioned quite a lot in the presentation. So is there any particular measurements that maybe people could add that would?
It's a very tricky one to ask, or not to ask, I know, but a very tricky one to answer. For me, when it comes to this, if you consider the dispersal or dispersion or the source, it's individuals, it's point sources, and that's several or 70 point sources in a room, all behaving differently, and the source could be one of the 70. Again, it's about this complexity of positioning a monitor or monitors in location that is representative. And that's the really tricky thing we're dealing with, is that when you have point sources, line sources, volume sources, all these different types, the point source is the one that typically it's fine and you look at it as an individual entity. But when you have 50 students in a room, it is very difficult. I wish I had an answer. Probably have a paper on it if I did, I think, Daniel. But unfortunately, yeah, that's the complexity of trying to measure anything. Obviously, you want suitable air changes, so you can still do the obvious, I don't know, CO2 levels, is what, for example, is just as one. But again, you're only measuring in one or two locations, and that's not representative of the whole space. And that's where it's very tricky.
Okay, thanks very much, John. I think we've got around to most of the questions. Apologies if I missed anyone. If I did, we'll try and follow up afterwards. And as always, you can contact myself, or John provided his details on his slides as well. So feel free to get in touch if you want to ask anything further after. So I'm just going to finish up with a brief 2 minutes of closing announcements. Switch off my webcam again. So firstly, I just wanted to mention ASHRAE is hosting an indoor air quality conference, which was originally due to take place this year, but has been postponed to September 2021 in Athens, in Greece. And just highlight anyone that's interested in attending or submitting papers for that conference, it might be of interest. And they've also added 4 additional topics, particularly around indoor air quality and the theme of COVID-19. So those are highlighted in red on the slide. I was also asked to mention about technical committees, because I'm not sure if everyone's really familiar with how ASHRAE works in terms of its technical committees. So ASHRAE has a whole ream of technical committees on a range of different topics. If you go to the ASHRAE.org website, go to communities and technical committees, you'll be able to, if you're already an ASHRAE member, you can apply to join any of these. They're all free to join. They're all made up of volunteers globally. You can see a list of the TCs. I've highlighted the sections that they fall under, which for the most part kind of correlate with the 4 ASHRAE handbooks, if you're familiar with those. For today's audience, if you're interested in ventilation, there's probably a couple of key sections under environmental quality, load calculations and energy requirements, and ventilation and air distribution. And I thought I'd highlight TC, or Technical Committee 4.3, which focuses on ventilation requirements and infiltration. And that committee of volunteers, is solely responsible for putting together all of what you find in the ASHRAE Fundamentals Handbook, the most recent one, which was published in 2017, and also the standards that are published, the standards and guidelines from ASHRAE, like 62.1 on ventilation for indoor air quality. So yeah, if you're an ASHRAE member, I'd recommend signing up for technical committees, even just for your own interest. As soon as you sign up, you'll be included on circulation list, and you can contribute and attend virtual meetings whenever they're hosted, and even look to contributing in the future towards the handbooks or standards or guidelines from your own experience. I mentioned at some of our previous meetings, we've a newly elected ASHRAE Ireland board as of last month. So you can see the committee members and board here. As always, if you're interested in volunteering or participating, please just get in touch. And lastly, just if you want to keep updated with regard to our own events, series events like this, just make sure you're registered on our mailing list, and you can sign up as well to our social media accounts, Twitter, LinkedIn, and YouTube. And lastly, thanks very much to our sponsors and supporters that help make our ongoing activities possible. So thanks everyone for attending today. I'm going to close the webinar here. As I said, if you have any follow-up questions, feel free to get in touch with myself or John afterwards. So thanks very much everyone for attending. Bye for now.